Hey guys, we are ready to look at 2.7. I think so far things seem to be going pretty good. I am going to try to schedule a Zoom meeting for later this evening, sometime after I get home, or maybe even tomorrow, because I've gotten a couple of messages requesting that I record it because some people have to work, and I would much rather try to maximize our time by being able to address any questions that anybody has. But I'll figure that out here in a little bit. I want to get this video done and get it out to you guys so you can start working on these notes as well. Please keep the questions coming. So far, I think everything's working out really great. And we're just going to keep plugging along until you guys just say, hey, whoa, hang on. I don't know what's going on. But we're talking about, so the last set of notes we had, we looked at just how to use the normal curve and how to use the z-table. In this set, we're going to actually start applying that information to some practical problems. The first thing we want to look at, though, is we're talking about finding the percentage of a probability for a normally distributed variable. Here are the steps listed on how to do that. First, you would sketch the normal curve associated with that variable, shade the region of interest, and mark the delimiting z-values. So remember, if we're talking about the z-values, we're standardizing that variable. So we're looking at from -3 to 3. And it's going to be centered around the mean, which should be 0. Find the z-scores for the delimiting values found in step 2. We've done that already. That's where you have z is equal to x minus mu divided by sigma. And then use the table, just like we did on the last set of notes, and you can come up with that percentage. So here we have intelligence quotients are measured on the Stanford revision of the Binet-Simon intelligence scale. They are normally distributed with a mean of 100 and a standard deviation of 16. Determine the percentage of people who have IQs between 115 and 140. I'll sketch the normal curve here. So we're talking about, this is our normal curve, and we have these specific x values, but I want to normalize those x values to center them around a mean of 0. So to calculate those z-scores, so let's look at the z-score for 115. So we have 115 minus our mean, which is 100, divided by sigma, which is 16. And when we type that in on our calculator, we get 15 over 16. So as a decimal, it's going to be 0.93, well, 94. 0.94. So that's the z-score for 115. We also need to compute the z-score for 140. So that's 140 minus 100 over 16. So the z-score for that would be 40 over 16. As a decimal, it will be 2.5. So we have 0.94 and 2.5. So here's where the z-table comes in. So let's first find the z-score, or the probability for z being 0.94. With the standard table, we are going to look at the positive values on this one. So we're looking at 0.94. So right here I have 0.9, and here is 0.94. So that value is 0.82639. And switch over here. Whoops, wrong thing. Okay, so this is 0.82639. So that means that 82.6% of the data lies to the left of that z-score. Now let's find the probability for 2.5. Keep clicking the wrong thing here. So 2.5 would be 2.50 is 0.99379. So that's 0.99379. And that's the total value of all the data that lies to the left of 2.5. So remember what we're looking at here. If I shade this, So we'll say that this is 0.94 and here's 2.5. We're trying to find this region right here. The 0.94 gives us everything to the left of 0.94. The z-score for 2.5 gives us everything to the left of 2.5. So we're finding this region by subtracting the lower bound from the upper bound, and we would get 0.99379 minus 0.82639. I don't know what happened with that 6, but when I type this in, 0.99, we get 0.1674. So the percentage of people who have IQs between 115 and 140 is 16.7%, roughly. And that's how you use the Z-table in a practical application. When we talk about some specific values with the standard table, there is a special rule. It's the 68.26, 95.44, 99.74 rule. A lot of people just call it the 60, 68, 95, 99 rule. Those decimal values do become important though. But the first property of this rule says that 68.26% of all data lies within one standard deviation of the mean. Then we expand that out. 95.44% of all data lies within 2 standard deviations of the mean. And then finally we get to the 3 standard deviations to the left or the right, and that's where we get the 99.74. So the remaining values lie beyond those tails in the normal curve. Sketch it. Whoa, that is not a normal curve. Okay, if this is -3 and 3, that remaining value, the remaining small percentage of data lies in these little tails that are to the left and the right of -3 and 3 respectively. With example 2, it says, recall that IQs are normally distributed with a mean of 100, standard deviation 16. In particular, we have mu is 100, sigma is 16. Apply the 68, 95, 99 rule to IQ scores and interpret the solutions. So for the 68.26%, that is the data that lies to the left or right within 1 standard deviation of the mean. So to the left of that, the mean is 100. So how do I want to write this out so that makes sense? The left is 100 minus 16. That's 1 standard deviation to the left. The right upper bound is 100 plus 16. So that's 1 standard deviation to the right. So what we get is 84 to 116. What that tells us is that 68.26% of the population has a IQ between 84 and 116. Then when we go on and look at 2 standard deviations, which would give us 95.44% of our observations, it's 100 minus 32, which is 2 standard deviations, and then 100 plus 32. And what we get there is 68 to 132. So the interpretation is 95.44% of the population has an IQ between 68 and 132. And then the last one is 99.74, which would be 100 minus 48, 3 standard deviations, and then 100 plus 48, we would get 52 to 148. So now the interpretation on that one is that 99.74% of the population would be expected to have an IQ between 52 and 148. I don't know why I always end up typing these as TES, but anyway. So you can use that rule to find some very specific values or range of values on the normal curve to give you an idea of what's going on with the data that you perhaps are evaluating. Sometimes we do need to do the reverse of this procedure. We might know the z-score, or we might know the percentage rather, and we want to find the z-scores. And we're going to see that in example 3. It says to obtain and interpret the 90th percentile for IQs. So we need to figure out what z value would give us this 90th percentile first. So we're going to consult the z table, and to get the 90th percentile we're looking for a z value here in the middle of the screen that would be equivalent to 0.90. And looking right now, it's going to be somewhere between these two values, which is 1.28 and 1.29. So let's split the difference, and we'll say the z-score is 1.285. Clicked on the wrong thing again. So 1.285 is our z-score. So we're going to take 90th percentile, in case you were wondering, is equal to 0.90, which is equal to 1.285. That is our z-score. The formula for z-score, z equals x minus mu over sigma. So we know the z-score, and we want to find what the value is for x. We know that mu is 100 and sigma is 16. So this is just a simple matter of algebra. We multiply both sides by 16, so we get, eventually if I can get the calculator to work, 1.285 times 16 is 20.56 equals x minus 100. We'll add 100 to both sides, so we get 120.56 is equal to x. So the 90th percentile, we'll round this up to 121. So the 90th percentile means that if you have a IQ of 121, you have a higher IQ than 90% of the population. It also means similarly that 10% of the population has an IQ higher than 121, and that's how you obtain and interpret that percentile. The rest of this is your homework problems. There are only 6. Don't complain. They're just A and B, except for number 2, 3, and 1. But they're not that bad. You guys can do this. But like I said before, if you have questions, please ask. And I hope to see you guys either this evening or tomorrow in a Zoom class.